Well, hello, folks. We'll go ahead and get started. It's good to see you all. I'm looking forward to some additional interesting information that we're going to be covering today, and together to see the interesting things that we're developing with the project works that you're doing, and I'm sharing some of the stuff I've been doing for a while. But let's go ahead and open up in a prayer, and then I'll give you a sense of the material that we'll cover for today. Dear Heavenly Father, Lord, I pray that you would be working in each of the students' lives in this course, Lord, that you would help them to understand the material, that it can actually be motivational, maybe seeing things from a different vantage point. And I pray that as a result of this, that they can be better engineers and get a better understanding of what it means to be a systems engineer. Pray that you would help them in their time here at EPU as they're getting a chance to study scripture, that would be a profitable um, venture, and that they can be seeing how to derive the theological concepts from that material and give them interesting and creative ways for faith integration. In Jesus' precious name, we pray. Amen. Well, I was thinking about this and giving a perspective of, well, what is it that a system engineer does? And so with this chart, it kind of gives you maybe another way. If you just count the number of chapters in each of these sections, um, there is a real critical time for system engineers to actually be earning their paychecks. That's a term that I've heard sometimes, where you want to be finding these issues early on. And so if you just count here, there's 8 chapters that we have in this concept development, and we're going to be taking these one at a time. And then in the development, there is a partnership. And so maybe about a medium effort that you're doing versus the subject matter experts in specific areas are starting to pick up the things, maybe a little bit more streamlined in the operational mode, but there are some system engineers that are quite valuable in this area, in that system engineers can go from the very beginning of when an idea is formulated all the way to operational support. And with this kind of full life cycle experience, it can be very useful for them as they say if there's going to be a new block build for the things that they're working on. And so that's maybe a perspective that you'll bump into in the future. So what we're going to cover today is now the second chapter, where we're going to be talking about requirements analysis. And so one of the things that I recommend that you do with your 3 use case diagrams, and pretty much most everybody submitted that with a paragraph that was trying to describe what you're doing in that use case diagram, which ends up, you could be thinking of that as a use case story. Well, now what we want to be doing is taking that information and flesh it out in a little bit more detail. And this is going to be something useful in this part of it, where we start to do some requirements analysis. But let's get a perspective of what that actually means in the context we have in our textbook. And I've also included some material from our NASA System Engineering Handbook, and one other resource that I'll dwell on towards the end. It could give you an idea of what you might want to be utilizing thematically for requirements. So what is it for developing the system requirements? The objective of the concept exploration phase, as defined here, are to explore alternative concepts. And so you can have 2 or more. Typically, you have 3, maybe to 5 concepts that are competing against one another. And then what you're trying to do is derive the common characteristics and convert the operational oriented system view into an engineering oriented view. So a system oriented view is a fairly high level, and then when you're getting into an engineering level, it's more details. And so over time, you're trying to provide those additional details. Outputs of the concept exploration are the system performance requirements. And so here, these are high level requirements. Thus, we see the term system is a focus. We have a system architecture down to the subsystem level. And so when you have the system requirements fairly well laid out, then you can have a flow down of how that's going to work down to the subsystem level. And then finally, having the alternative system concepts, you want to have it finally boil down to these are fairly well delineated concepts that can go forward through the next steps in the rigor that you're going to be doing in this concept exploration phase that we're working on. So the activities that comprise the concept exploration are the operational requirements analysis. This is done to ensure the completeness and consistency. I can tell you, I've been in a lot of meetings where we do requirements analysis. Implementation, concept exploration. And so this is where you're refining the functional characteristics. Okay, I can see that this is what you want. You want to have 24/7 coverage. You want to have a resolution of those sensors to be able to have a certain amount of fidelity. And so this is where you start to be fiddling with the concepts to see, well, what exactly might that mean? So with some of the things that you all are working on, how much power is needed for a nuclear power system, for an electric vehicle? Well, what kind of concept are we going to have? How are we going to be doing an autonomous operation? What kinds of sensors? What kind of vehicle is going to be look just like a gas-powered vehicle or not? Tesla, in some basic sense, it's similar to a standard car, but when you start to sit in it and start to operate, you can see that there are some distinct differences that they decided to go with. Those are just a few threads. Then we get into the performance requirements foundation. This is the deriving the functions and parameters, and we're going to have something called a parametric diagram. What are the physical equations that have to be obeyed and accounted for when we get into more specific details of the design? And then we want to do the performance requirements validations. We want to ensure the operational ness that they can actually do that, and we need to be validated. So those are the kind of things that are going on. So back to our our overall phase diagram, and with this concept development phase, we're getting a little bit more specific. And so we talked about needs analysis. Now we're getting into concept exploration. And the three things here were requirements analysis, the focus of this chapter. We want to be doing concept synthesis and then feasibility experiments. So from the needs analysis, we started to articulate in more details, well, what are the system capabilities that we would like to have? What are the system operational effectiveness that we want to make sure that it has? And so I mentioned nuclear energy, I mentioned an autonomous vehicle. So maybe for some of this would say for the missile silos that Nathaniel is working on, the system capabilities is it's a 24/7. It needs to have a response in say less than 2 minutes. And so then you have to determine, well, which missile silos might be activated under what kind of scenarios, how many missiles would have to be launched. And so that would be another possibility. And so Kyle, with what he's doing with satellites, we're going to be getting into this more in detail. At the end, there's going to be a summary chart, but the example that I was sharing with you last Thursday was some of the use case diagrams for a space-based fire detection system. And I'm going to be coming back to that, and hopefully that will help fill in the gaps. So after we've done this, then we're going to be coming out with the candidate system concepts. And so, and then it could be one or more possibilities that we are going to continue to be playing against one another. And then we have the requirements that are fleshed out. Now we know what it is that we would like to accomplish. We started to have a more targeted sense of what are the candidate concepts that we're going to be leveraging. So last time we were just focusing on the needs analysis, and we were only at the system level. Now we're getting into more specifics about thinking about the system. They identify, explore, and synthesize the concepts. So we're not just back of an envelope or napkin where you have just a few squiggly lines that's trying to give you an idea of what it is. We're more specific. And now we're getting into things that bleed into the subsystem where we define the requirements and ensure the feasibility that it is actually going to work. Just to give you an idea, a satellite is thousands of miles away. And so it's not going to have the ability to zoom in as if I'm going to be doing a close-up shot if I'm thinking in terms of an optical sensor. It's going to need to have a lot larger aperture for it to do something similar. And there's other characteristics that come into those types of things. So this is where we start to be fleshing out. If we want to have a space-based system, so this is more what Kyle is dealing with, then that gives some cause and effects. For Abby within a electric vehicle, how heavy do we want to make the car? And so if we want it to be less than 10,000 pounds, and we know that batteries weigh so much, it's going to give us an idea of how many batteries we can have on that. And that's going to tell what is the total kilowatt hour capacity that vehicle is going to have. It's going to have 50 kilowatt hours, 75, 100. Those are some examples. Well, this is one of the illustrations from the System Engineering Handbook that I thought was helpful. And we have talked about spiral development as one of the ways that this can be done. And so what I'm just showing here is just to give you an idea of how we can start out from a high level way of looking at this and gradually go through these different things. And so identify and quantify the goals. We can create the concepts, do the trait studies, select the design, and then increase the resolution. And so when we're increasing the resolution, now we go and have a further resolution of the system. And so maybe if I start out with an optical system going back to a space-based system, now I'm going to be making a decision, saying like going from the Hubble to the James Webb Space Telescope, that it turns out that we have some fairly good coverage in the optical regime. We want to be going things into the infrared. That's one of the distinctions between the James Webb Space Telescope. And so we go to this level, and then we go through this process. And so maybe the next level is, well, how large of an aperture are we going to allocate for doing this? And so that's something that could start to go out. And so we can have multiple layers that are being part of what we're doing. Give me just 1 second. My wife and I love our cats, and they love to be in the center of attention, and we love it too. But trying to focus on you guys. So that was Daisy, in case you caught a glimpse of her in my camera. So that's just one perspective I just wanted to think about with this spiral diagram. It might be another way to give you some insight. Well, let's think about the requirements, development, and sources. And so I've already been talking about requirements. It's a vitally important area and something that can be very challenging. And so this is one of the things that's important for system engineers to be able to master and to do well. So requirements can originate from a variety of sources. The author can rely on knowledge from existing system deficiencies, as well as evaluating novel concepts to derive requirements for the users to succeed in their future missions. And so that's a rich area. You know what the requirements were for the last system. So I've talked about GPS. And so say if you wanted to go from GPS 2 to GPS 3, or now from we're more in the area of going from GPS 3 to GPS 4, that can help. 4 general approaches include the development of a new system to operate in a future environment, usually as a result of new technology or concepts. The GPS satellites are in a medium Earth orbit, maybe with new technology, they could either go to a low Earth orbit or a geosynchronous high Earth orbit, and maybe you don't need as many satellites. That you can be dealing in the area of improvement, given the existing system. Consumer demands can identify new ways to improve the existing system. It can be threat driven. New threats require re-examination of existing systems and concepts with improvements to counter these threats. And finally, additions. You can have new allied or complementary systems are introduced, enhancing the original system, but requires a new way to interface and operate. So let's say that you're going to be adding additional capability. And so whatever way you want to be thinking about it, there's new technology for nuclear power control and operation that you can increase the output by a factor of 2. And not only for providing power, maybe with some of the excess heat that's made available, that you can actually provide heating for the local neighborhood in a safe way. I've heard that for like data centers, there's a new data center that's going up in the UK, and that's one of the serendipities that's going along for that. That may or may not be applicable for a nuclear power system. There may be other concerns that might not allow it to go in that direction, but I'm just trying to think with you and have you guys thinking about it within the sense of what you're doing with your specific projects. So we've had this diagram before, but now we're getting a little bit more surgical, getting a little bit more in depth. And so this is dealing with the requirements. And so we have the operational requirements. So the inputs would be things coming from the predecessor system, things that the needs analysis have clarified and are giving you more specifics. And so then we're doing this operational requirements analysis to get this in a better, more usable way. So we have that operational requirements. Then we have things that we're going to now get into the performance requirements formulation. So how well does it perform? Is it going to actually meet what the customer wants? And so maybe you would be going between requirements and those use case diagrams to have a discussion about that to see where it is. Then we get into the implementation. How can we go about implementing this? How are we going to parse these things into elements? Maybe there's some existing major configuration elements that you want to leverage as much as possible to minimize the cost impact. That might be something that would constrain this a little bit in terms of implementation. And then finally, we do the validation. Now that we know what the performance is, we have an approach for doing the implementation. Now we want to see, well, how would we go about validating that? If it's operating in space, we don't live in space here. And so we have to mock up space environments and then test it to make sure that it's going properly. So that would be, once again, an allusion to a space mission perspective. Well, what about the requirements, features, and attributes? A feature is a set of requirements that will satisfy an objective, which is typically at a high level of abstraction. And so I've used that term OOSM, object-oriented system engineering method. And so this high level of abstraction is really a good place to be starting and a sweet spot for what system engineers do. These features may vary between requirements users and the system needs, but may be useful to organize sets of requirements in order to describe their performance to a set of specific users. A collection of these features can then be developed to ensure the proper set of stakeholders have been adequately consulted to satisfy their specific needs. So Nathaniel has probably fairly clear what the requirements are, since this is something that the US government is contracting to do this capability. If you're doing a nuclear power plant, there's going to be regulatory agencies that are going to be specifying this. And so a big part would be producing the energy, another part would be safety and and other kind of protocols that that would be part of that. And so these collection could be binned into something like that, aspects of the capabilities that are going to help you to perform, and other regulatory things that may come into play. Requirement attributes describe the technical composition of the requirement. It is measurable, it is quantifiable, it is under what conditions, and qualifiers is the requirement satisfied. And so this has to be determined to give a manner in which you're going to be able to come up with a validation approach. Okay, here's just a two charts that are back from our NASA System Engineering Handbook. And so this talks about the elements of a requirement. And so they use this term metadata, requirements metadata. Maybe some of you have heard that term before. Meta is kind of like below, or there's like tags, and then maybe you can think of like a dictionary maybe as a meta. So the word, and then you have the definition, but you just have one word, and it gives you a more detail. If you wanted to get more of that information about, well, what is the essence, give more richness to what that one word is all about, you could be looking it up in the definition. So here are the things that you have. You have a requirement ID. And so it has like whatever you want to think of it, a phone number, a unique number that's associated with whatever it is. What is the rationale? It provides additional information to help clarify the intent of the requirement. Traceability is important. And so maybe what we're doing now, we're at the very top. Maybe if you're having something, a large acquisition from a government entity, or maybe a company, they're going to give you a top level requirement. And so that's going to be your highest level trace that you're going to trace from. You have this idea of an owner, the person or group who is responsible for writing, maintaining, or approving changes to the requirement. Verification. So these are things like test, inspection, analysis, demonstration. And so we'll be showing an example of a verification matrix. And so the method would have this, either a T for test, an I for inspection, A for analysis, D for demonstration. Who is a verification lead? And so is this something that is demonstrated at the subsystem level? Does it have to be done at the system level? And so you have the lead, who that person is that's responsible, and then what is the level? Both of those things are part of requirements. So what are the benefits of a well-written requirement? It establishes the basis for agreement between the stakeholders and the developer. That's important to do. It reduces the development effort because less rework is required to address poorly written, missing, and misunderstood requirements. If you have a really well thought out requirements, it's going to be clear to those that are implementing them what they're going to be do. It's not going to be subject to coming up with two different interpretations. I actually encountered that once in an early operational compatibility test, and there was a modulation technique that was being used, and the two parts of that communication system misinterpreted. So one interpreted this way and the other person interpreted that way, and it didn't work. So it's good we had that early operational test rather than having it at the end, that they could figure that out and fix it. You want to provide a basis for estimating cost and schedule. This is really important because this can actually influence what you're going to be doing in terms of going in one direction or another. You want to provide a baseline for verification and validation. You want to facilitate transfer and then serve as a basis for enhancement. So those are just some things from the NASA perspective that I wanted to highlight. Well, let's think about the requirements development process. And requirements development involves 4 basic steps: so elicitation, analysis, validation, and documentation. So you can think of it as a flow going along these things. this way, these steps will be done correctly, lead to a robust set of well-articulated requirements. In our textbook, it actually there's some iterative flavor to that you come up with an elicitation, you propose things, then you start to play without requirements. You may have some mathematical model. So our model-based system engineering could be helpful here, and you can validate and iterate it. And so then you can say, yeah, it's validated. The requirements analysis, yes, this is good to go. And then you finally get to a point where you can say, well, let's document it. We'll take it to the bank. We're ready to go forward. Well, this is another chart from the NASA System Engineering Handbook that I thought was interesting to maybe give a perspective that you might not have thought about. And so we have this idea of a flow, a type, and an ownership. And so first of all, we have something at a higher level, program requirements, and below that, a project requirements. And so this would be a lower level part of this system. And so you can have things that are imposed by the stakeholders. And so the highest level in NASA is something called a mission directorate. And there's several mission directorates. If you go to nasa.gov, you can see some of that. And so they're going to give you this top level requirements. And so the top level governmental agency is pushing things in, but then you can have self-imposed, and those can be flowing down to the lower level. Those are all possible. And you can have a mixture of technical and non-technical requirements. And so one of the things that they were mentioning here is the spacecraft shall provide a direct Earth entry capability for 11,500 meters per second or greater. So this is something that's coming really fast, coming to the Earth, and we need to be able to catch that. And so there needs to be the means to be able to do that. And so that would be something that this could be a push-up, that there needs to be some cooperation between things. And so the green or technical, that would be more technical. You could also have non-technical, at least one major element shall be provided by an international community. You might have direction that you need to have some collaboration among multiple things. So this is just a little bit, some insight of what's going on from a NASA perspective. We also have a hierarchy. Requirements are organized into several different levels in order to develop requirements for the proper scope. What we have in our major textbook, it organizes requirements into operational, system, performance, and components. And so these are some more details for each one of those. Operational requirements are described of what needs to be executed within the scope of operation. System level requirements are more focused on the system and how it performs the operational environment. Performance level requirements are stated as required outcomes of the system. So it needs to make sure that it's producing this, typically stated in terms of engineering characteristics. And finally, component level requirements are focused on the technical aspects of the system and will be at a lower level of technical detail. From our NASA System Engineering Handbook, this just gives you an idea of the how things are flown down. So you can have a mission authority. It could be some senior office within NASA, could be other folks, the science panels that are run by the National Science Foundation. Maybe you have some other mission partners, and this is gradually flowing down here. And so above this dotted line are the customers feeding into your system. Then you're looking at the system functional requirements. This would be the top level. And so this is then pushed down to the system performance requirements. And you have things at the subsystem level and things that are allocated below that. There can be some iterative process that you can finally see here, that can we actually solve this overall performance? And so a system engineer has to be taking things from subsystem A, B, C, and other things, and do their analysis and say each one is meeting their allocation. We can actually meet these requirements, and so all of this looks good. or maybe there has to be a reallocation that the way that we functionally broke it up is not going to quite work the way we hoped. And so we'll just have to modulate that to some degree. Well, if we have requirements, then we need to have a measuring stick to help us figure out, well, how good how well they're performing. And so metrics are used to inform the analyst, engineer, and decision maker whether or not the system will successfully accomplish its intended objective while in an operational environment under operational conditions. And so we have these things here. We have the measure of effectiveness and we have the measure of performance. The measure of effectiveness, or MOE, refers to a qualitative or quantitative metric of a system overall performance that indicates the degree to which it achieves its objective under specific conditions. And MOE always refers to the system as a whole. So that's a top level metric. And then we have a measure of performance, or MOP, refers to a quantitative metric of a system's characteristics or performance of a particular attribute or subsystem. So this is going to be a lower level. And MOP typically measures a level of physical performance below that of the system as a whole. Okay, I'll just finish up, have two more charts, and then I'm going to give you an example. And so we can have a little bit of a conversation about that. And I'll be going between a summary chart on that and some of our model-based system engineering things that we're working on together. So we have our requirements now. We've been able to figure them out to a greater degree. Now we need to be figuring out the verification and validation of those requirements. Performance requirements validation involves two interrelated activities: the integration of requirements derived from alternative system concepts and the effectiveness analysis to demonstrate satisfaction of the operational requirements. Performance requirements are defined in a living document. And so there is an iterative process that you're going through this life cycle as you're getting to a final point where you've got your design and everything is ready to be delivered because you've been able to build everything. Everything was running according to spec and you'll be able to validate it. Requirements are reviewed and updated throughout the system life cycle. And so there are a couple possibilities. I'm more familiar with this first one, the top-down system engineering, TSE, versus an agile method. The traditional waterfall technique may progress through a more methodical approach towards requirements development, but may take longer, and it usually is. And so when you have a large enterprise, millions or billions of dollars going into a system, you're going to be more methodical and making sure that it all comes together in an appropriate way. Another alternative is an agile technique that iterates through the development much quicker. And so if you have something that's of modest complexity, it's going to be a lot easier to do things from that point of view. Okay, I'm just going to go to the summary and then I'll go to this other chart. So what have we talked about? We've been focusing on requirements. And so we started out with thinking about developing the system requirements. We discussed the requirements development and sources. You're going to get sources from your stakeholders, and they may have some general tenets that they're going to say have to be part of your baseline. We talked about the features and attributes of requirements. We then got into the development process and how you can have some iterative manners in which you're going to be looking at that. We talked about requirements hierarchy. The top level requirements are at a higher level than the subsystem or the component level. We talked about metrics, the MOEs and the MOPs. And then we got a chance to get some insight into the verification and validation. We talked about the difference between top-down system engineering and agile. And most of what we're going to be talking about as we go through our courses in this top-down system engineering methodology, but also thinking about how model-based system engineering can help. Now, I realize that what I just shared, that's a lot of information. And hopefully with this and some of the stuff that we do in our project work, it's going to make it a little bit more manageable for us to get a get our head around that. So this is in a tabular form of the top level space-based forest fire detection system that I'm using. And the more enterprise tools, sometimes I've heard it Cameo, but it's gone through so many name changes. And so I'll show that in a minute. And so this would be an example of the capture of requirements that would be a really good way of having what you want to be doing with each one of your systems. And so this is what I'd like to be spending some time getting some discussion about. And I'm going to come back to this chart in a little bit, but I have it here in a PowerPoint chart, but I'm also going to be sharing it with our tools. And so I'm going to go ahead and switch the screen that I'm going to share. And are there any questions on what I've covered so far? Let me just double check that. Maybe just give me a heads up. Does that, you guys tracking what I'm saying? You can do a thumbs up, thumb down. You can just go off mute. Okay, good. Most of you guys are following along, and this course is really, it's one of the ways I can be thinking about it. It's like a survey of system engineering, and so I'm hoping to give you a working understanding of what that is all about, and I look forward to having us work this out together as a team. Okay, well, I'll just spend just a few minutes, and then I wanted to have some conversation with all of you. And so let's review another way of thinking about this system that I began to introduce last week. And so from my PowerPoint chart, this is stuff that the space mission engineering, the new space mission analysis and development textbook has this material, and Freudenthal and others created a book that focused on this. And now we're using this as one of the ways that we're going to be going through the material to give an idea of how we're going to define the system. And so at a very high level, this would be a simple use case diagram, and then I'll show you a more elaborate one. And so what it is that the Forest Service needs to have the ability to detect and monitor forest fires. And now we get more specific. We have now just a domain in the US and Canada. They're going to, and part of that is they're going to provide operators. And so federal employees from the Forest Service are going to be taking advantage of this. They need to be provided with forest fire data in near real time. And so this is going to be in collaboration working with the fire department. My wife and I recently watched a movie. I think it's called Hot Shots. Anyway, it's the specialized firefighters, instead of like going into the forest where it's burning brush and just spraying it with water, they actually try and rob the fire of the fuel it needs to have it continue to progress. And so they actually do these strategic burns so that the fire will come to a point, and since the fuel for it to continue to burn is gone, and there's like a gap, it actually burns out. And that's sort of a technique that they would use. And so you can see that getting this information about forest fires would be quite useful. Now, you can just hear from my dialogue there that I've actually started to articulate this in a user story, and that can be the basis that you would then go next to be giving some more details. So we have that information, but we also want to be archiving that data. So say you have a really bad fire and you wanted to analyze, what did the fire department do? How do they interpret this forest fire data? Maybe there needs to be a change in tactics. And also it wants to be doing monitoring and maintain healthy and safety of the system itself. That could be another thing that would be part of the things that they would be thinking about. So you have more conversations and they actually give you some more requirements. That's very common when you start to be working with stakeholders, that they give you that kind of information. I'm not going to get into this, but there is also a lot of other care and feeding that needs to be going on for the system. So each one of you, how often do you have to take your electric vehicle in for servicing of one type or another? Your nuclear power plant has to be constantly maintained. Maybe there's more fuel rods that have to be put in. The old ones have to be decommissioned. For the missile silos, they have to go through a retrofit every, say, 25 years. And so you have to make them for maintainability. And for Kyle, looking at satellites, the stuff I've been covering here is the kind of things that you would likely be bumping into. Okay, let's show this in a table form. This is the table form of these requirements, and this is what we're going to be doing in visual paradigms, something like this. And so what is the hierarchy of these requirements, if there is any? This is pretty flat. There is just a few examples here where there is underperformance. There's weather, resolution, and geolocation. And so you can see by these numbering conventions, these are sub-requirements of that. And so for this example, that's the only time that that shows up. So that's what I wanted to do to maybe just set things up. And I'm going to stop sharing my screen now. And we can have a dialogue. And you guys tell me, how's it going for you of thinking about your use case diagrams? Maybe you're still finessing them. And how are we going to translate that into requirements, which is the next step?
How many requirements do you want?
I would like to have at least 10. That's, you can even see here, there's like on the order of 20, and these are top level requirements. So at least getting at least 10 requirements is what would like to have people be developing. Anybody want to give an idea of what they think would be a requirement based on what you've seen from your use case diagram, what you've seen from what you've been exposed to so far? There's a term called a key performance parameter. What do you think would be a key performance parameter? Maybe I can at least help each of you come up with a good way of thinking about that. My soundtrack that I've been giving since I've been informed what you guys are doing in your project is one of the ways that has helped me to figure that out. Nathaniel, do you have an idea of what you think would be a key performance parameter for your missile silo project? And remember, it doesn't, I'm not asking for a fully fleshed out answer. We're talking, and a lot of times system engineers, that's what they do. They talk, they refine, they discuss. And so this is part of what we're doing here.
Well, overall, I think I'd want some sort of maintenance crew on there, and I'd want them to have some sort of interface that they can interact with, something that's just kind of showing the levels of everything.
Mm-hmm.
I think like that would that would kind of be the performance thing to me, is that panel all checks out, and if
Yeah.
something doesn't, then they go fix whatever that thing's telling them is bad.
Mhm. Yeah, well, let's build on that. So I think that's a good idea. So various systems that I've worked on, they'll have like a summary display that's showing the status of the system.
Mhm.
And so I think that's what you're getting at, Nathaniel. And so operators, they can get the big picture and know what's going on and how to manipulate that in an effective way. Am I kind of capturing what you're saying,
Yeah,
Nathaniel?
yep, exactly.
Okay. So the next thing that you want to be thinking, first of all, write that down
Mhm.
in any form that you want. Just put it down in a narrative. The next step will be to start to put that into a requirement language. And so requirement needs to be a simple sentence. Each missile silo shall have a top level status display.
Mhm.
Something like that. Okay.
Got it.
You could have sub requirements under that. It's going to be indicating the then what are the this is where you start to be fleshing out the concept a little bit. Well, what is a missile silo? Does a missile silo only have one missile? Maybe most likely that's a case. Is it constantly maintained with its fuel, or is that how often is that fuel changed out? Maybe there's different criteria. There's different aspects of readiness. The warhead that has to be serviced or checked periodically, the security measures that are associated with that. There's a term called surety, where you want it to work when it's supposed to work and not blow up when it's not supposed to. And so there needs to be some sophistication in the design that's associated with that. So that would be some examples of things that you could be focusing on. You focused on the missile silos rather than the missiles. And so we want to be thinking it from that point of view. And so let me move on to some others. And Jonathan, do you have any idea what you think an example requirement might be for key performance parameter for your nuclear power system?
I was thinking like through the safety requirements, and so one major thing that I was thinking of, there should probably be like an automatic emergency shutdown in the event of something like completely going wrong or like natural disasters or around that area.
Yeah, definitely do focus on that because like some of you are working with some things that have some health and hazard potential. You don't want a nuclear silo to launch and then hit Hawaii or something. You don't want a nuclear power plant to have a meltdown. So those all are important. But I'd also encourage you trying to think of, well, if you had to have one requirement that gives the essence of what the capability of your system is, try and think about what that would be. But that's a good one, Jonathan and Nathaniel. I think you come up with some stuff that makes sense. Abby, what do you think would be a requirement that is noteworthy that you would want to make sure that your Gecko electronic vehicle is going to have?
I guess things like weight and then like the battery,
Mm-hmm.
and then I don't know how to word the programming for the self-driving part as a required.
Once again, the term that we have introduced a couple times, this idea of abstraction. So if I'm not sure the details, maybe just try and bring it up a level. And so you could just have it a very simple that the electronic vehicle shall have the capability for autonomous operation. So you could start at that level. You could have a sub requirement. One of the things that you might be sensing, and this is actually useful, this actually takes some thought. And so that's what system engineers have to do. They have to be thinking diligently, in depth, integrating a lot of things together. And so just like Abby's example, she needs to be worrying about battery technology, electronic motors, autonomous operation. Those are some things that all have to be coming together in an appropriate way within this design. Kyle, why don't you give us your thoughts on what you think would be a key requirement that you would like to focus on?
Well, the main thing is that I need to make sure that the power stays above 0,
Mm-hmm.
because if it goes off, then there's no one to turn it back on again. So,
Kyle, that's an extremely useful point. And so this is one of the things that as you have these use cases and other ways of getting a chance of understand the operational sense, like a CubeSat or a satellite or anything, once it sits, miles and miles away, you can't ever touch it and fix it. So it always has to maintain a reserve of power so that you can resurrect it from a worst case situation. So that's actually a good requirement, Kyle, that you can be focusing on. I know you wanted to be focusing on the power system. And so that would be a useful thing for you to make sure that you utilize. And also try and think of the linkage between your use case diagram and what you want to be doing for the requirements. And that's gonna be our next step in our development. Okay?
okay.
Well, good. I made a quick round the room for all of you to give you a sense of what you need to be thinking about. And now we've been introduced to two of the things that we deal with in model-based system engineering. I haven't been showing you my visual paradigms, but I'll show you this. And this was a diagram that I always already let you guys see. And so right now, this is a flat. This is like what we saw from the Cameo. So this is within the tool. There's just a few that are at a second level, which we can see here. But most of them are at this top level. And for now, it's okay if you have them all at a high level, but if you think about it, you can think of how one thing might relate at a lower level, you can do that. As long as you have at least one of these requirements, if you go to the modeling tab and you go to the requirements list, this is what it's going to show you. Can one or more of you guys just verify that this actually works? I haven't, since I now have the modeler, it's the first paid version. So it's above the community edition. Are you able, if you go to the modeling and then click on the requirements list, does it show a table like this? And if you guys don't have a requirement, just tell me that, and we'll go back to the requirement chart, and let's get each of you at least having one requirement to get you seated with that part of our development. So just give me some feedback where you guys are at. Okay, Nathaniel, so you get it, you do see the requirement in this table. There's not much you can do about it, but I'm not gonna force you guys to be paying a lot of money for something when there's not anything there. That you can see, like, there's the name, there's the ID. You can see the supporting use cases. You can have that kind of connectivity that would be possible if we were to be going into some more details there. Anyone else have, well, let's do this way. Give me thumbs up if you have at least one requirements in a, requirements, diagram. I think Nathaniel does, and if nobody else does, then let's go through how we make a requirements diagram, and I'm gonna have you guys do this with me. So let's do a new diagram. And so if you just type REQ, you'll get a requirements diagram. So what I tend to do is I start with the short acronym for what type of diagram it is. And so this would be maybe I'll call it CubeSat. KPP stands for key performance parameters. So and then you could just be putting in a requirement. So I'm just going to call this a CubeSat mission. Okay, I just put that the CubeSat shall perform its sensing and communication mission. So let me just kind of give you a sense of what I mean by that. Let's look back at this tool and remember what we have from this analysis done that's based on this textbook, and it is detecting and monitoring forest fires. And then we have at this highest level, it's the mission requirements. So you could call it mission requirements if you want. So maybe I'll just say CubeSat mission requirements. So for that would be something similar for Kyle. For Nathaniel would be missile silo mission requirements. Jonathan, nuclear power plant mission requirements. Kyle, it would be like this, CubeSat mission requirements. And then you're going to tie things in below that, make a new requirement. So I'll just make something for fun. So it's going to do great stuff. And then I'm going to associate this with another requirement. Do great stuff. And voila. That's how you link those together. You guys, everybody follow that? Let me just give a thumbs up if you're seeing that. Okay. Kyle, is that working for you? Okay. Well, I'm just trying to do this more in a lab way that we can be doing this together. And I think this might be a good breaking point. And so we'll pick this up again in earnest next Thursday. But we'll continue our journey going through the lecture material for the most part next Tuesday. But this is kind of where we're at. And so we're being challenged to think about this. It's amazing that the internet is what, like 25 years old now or something like that. It's much easier to do research. And so you guys can be trying and get some information if you don't already have it about your project. You know, get some information, from about nuclear power sites. You can go to DOE.gov for missile silos. It might be an interesting thing for you, Nathaniel, to see what you can find in the open internet to give you some perspective. And for Abby, even if you were to look at things from Tesla or that would be maybe for the electric vehicle. The Google car was a really good development. I think it was now it's turned into a subsidiary of Google, and I've forgotten the name is off the top of my head. But there might be just some key things. Just do a little bit of research to maybe give you a basis so you can be better informed as you're trying to flesh out what you would like to be doing. So I encourage you to just spend a little bit of your time on that front as well. Okay? All right, I'll stop sharing my screen. And I hope you guys all have a wonderful rest of your day, and we'll be talking soon, and I'll look forward to seeing you all on Tuesday. And send me an email if you have any questions.
Do sub requirements also count as requirements or?
Yes.
Okay.
Yeah,
I'll double check.
I would recommend that you don't put everything connected to that status display, that you maybe think of one or two other areas.
Oh, yeah.
But you could just a total of 10 is what I'm looking for, is just as a rough milestone. Okay.
Okay. Sounds good.
All right. Well, you all have a wonderful rest of your day. Take care. God bless.
Thank you, Professor.
Thank you.
Thank you.
Thank you.